Hey, hi everyone. Welcome to the last fourth seminar of the semester. Today we have Damanveer Grewal from our very own Arizona State University discussing some cosmochemistry related research. But first, I wanted to remind you that to stay up to date with what's happening with Force, you can follow us on our various social media platforms. You can also join our mailing list by going to force.asu.edu/contact. And of course, this meeting is recorded and will be available on YouTube along with the recordings from all of our other seminars. If you would like to give a future seminar yourself or suggest a speaker, please go to bit.ly/force seminar suggest. Let us know who you would like to hear in the fall. All right, and with that, I'll turn it over to Kisei.
Hi. Um, Let me introduce Professor Damanveer Grewal, today's speaker. So Daman obtained the bachelor and the master in IIT Kharagpur, and after that experienced a chemistry teacher, a high school chemistry teacher, and after that he decided to pursue the research, and he entered the Rice University and completed a PhD program in 2021. And after that, he moved to the Caltech as a postdoc, working with the Professor Paul Asmo, and now he's a professor, assistant professor at ASU. And actually, he will be moving to the Yale University as a faculty member in 2 weeks. So he will summarize his research throughout his PhD, throughout his work at ASU, and probably uh, also work throughout his work. So Dama, you can start.
Okay, can you guys hear me right now? Okay. All right. Thank you for the introduction and thank you for the invite, Kara and QC. Today, I'm going to be talking not about a specific problem that I have worked on over the last few years. I'm going to be talking about the general approach, how one can use some experimental data in combination with meteorite record, and I'm going to be primarily focusing on the origin of Earth's three key life essential volatiles: nitrogen, carbon, and water. Most of my talk, because I think this is a high pressure audience, so I have to give a big primer on cosmochemistry and sort of things to help you understand these problems, the problems better. And then hopefully I'll be able to convince you that how high pressure experiments in combination with this very specific, special kind of meteorites can help us understand the meteorite record much better and can help us gain some very useful constraints on the origin of volatiles on Earth. Okay, so we know that Earth is the only habitable planet that we know of in our solar system and beyond as of now. In addition to the presence of sufficient liquid water, the composition of the Earth's atmosphere, primarily composed of nitrogen with some trace quantities of carbon, plays a critical role in defining the habitability of a planet. Also, nitrogen, carbon, and hydrogen, all these volatiles are important, and they are important components of the building blocks of life on a planet. If we truly want to understand the habitability of a planet, we need to understand the origin of these three key life essential volatiles on the surfacial and the atmospheric reservoirs of our planet. But we also know that Earth is a tectonically active planet, which means it is the composition of the Earth's atmosphere and the surfacial reservoirs have been perturbed and has been determined over billions of years of Earth's history between the exchange of volatiles between the Earth's interior and the surface reservoirs. Therefore, if we truly want to understand the origin of volatiles in the surfacial reservoirs of a planet, we need to understand the origin of volatiles in this big box over here, termed as the bulk silicate Earth, which comprises of the mantle, Earth's crustal reservoirs, the surfacial reservoirs, the atmosphere. So anything in the Earth except the Earth's core, which is maybe exchanging some stuff with the Earth's mantle. But for the talk today, we're just going to take core as an isolated reservoir. So we're primarily going to be focusing on the origin of volatiles in the bulk silicate Earth. So this is where the cosmochemical idea comes in. So basically, if we want to track the origin of volatiles in the bulk silicate earth, so let me just get the pointer in. Okay, so if you want to understand the origin of volatiles in the bulk silicate earth, the general idea is that you take the isotopic composition of volatiles in the bulk silicate earth, and then we compare it with different cosmochemical reservoirs. So this is simple isotopic fingerprinting. And for notations, so on the y-axis, you have stable isotopic composition of nitrogen 59 by 49 in particular sample normalized to some standard, which is the atmosphere over here. And so on the y-axis, you have the nitrogen isotopic compositions of different cosmochemical and terrestrial reservoirs in per mil notation. And on the x-axis, you have the hydrogen isotopic compositions. And if you look at this red color star over here, this represents the nitrogen and hydrogen isotopic composition of the bulk silicate earth. So what you see in this particular plot is that the nitrogen and hydrogen isotopic composition of the bulk silicate earth is distinct relative to the nebular gas. And even though there might be some overlap of the hydrogen isotopic composition of cometary reservoirs and nitrogen isotopic composition is distinct. So whatever evidence we have from the cometary reservoir as of now, and whatever evidence we have from the nebular gas, what we can say is that that the volatiles in Earth or the bulk silicate Earth were neither inherited from the nebular gas nor from the cometary reservoirs. But if you plot different classes of chondrites over here, we see that they broadly plot in a similar range. So no given class of meteorites is an exact match for the nitrogen and hydrogen isotopic composition of bulk silicate Earth, but they broadly plot in a similar range. So this has been used to argue that volatiles in the bulk silicate Earth and these chondrites, which sample the primordial materials in the first planetesimals in the early solar system, they had common origin of volatiles. And if you plot carbon over here, you'll broadly guess the similar kind of a picture. But if you look at the abundances of the volatiles in the bulk silicate earth normalized to these very primitive chondrites, we see that the volatiles are extremely depleted in the bulk silicate earth relative to primitive chondrites. Carbon and hydrogen are approximately depleted by 1.5 to 2 orders of magnitude. Nitrogen might be depleted up to 3 orders of magnitude. There are errors with like what these exact numbers are, but broadly you see this extreme volatile depletion. So you have two contrasting levels of evidence over here. On one hand, you see that the volatiles in the bulk silicate earth and these very primordial chondritic materials had common origin of volatiles. But on the other hand, you see that earth or the bulk silicate earth is extremely depleted in these volatiles. So if we look at chondrites over here, this is a very simplified image of a very specific kind of chondrite over here. So this is a sedimentary rock. You could simply imagine it such, which is comprised of several disequilibrium assemblages. So you have CAIs, you have chondrules, you have metal. All of these three reservoirs are extremely volatile depleted. And then there is this dark colored matrix that kind of binds everything together. It's extremely unstable to heating and aqueous alteration. And all of the volatiles, carbon and nitrogen, are present in this dark colored matrix as organics, while water is present as this phyllosilicate minerals. And if you look at a planet like Earth, this does not look anything like a sedimentary chondritic reservoir. So what you have over here is a differentiated body, which is comprised of core, mantle, and crustal reservoir. So basically, you would have to go through a series of igneous processes, starting from some chondritic primordial materials in order to establish the volatile inventory of a final eventually forming planet. Therefore, if you truly want to understand the origin of volatiles on Earth, you need to track this journey from these very primordial materials sampled by chondrites to eventually fully formed planets. And this journey can be simplified by this very basic, very simple schematic over here, where you have primordial gas and dust exchange in the early solar system. So the dust probably is maybe could be have a pre-solar origin or could also have a condensate origin in the nebula. And then somehow these dust particles clump together to form planetesimals, probably during streaming instability. And because some of these planetesimals form so early, they inherit a very important short-lived radioactive nuclide. And that radioactive nuclide is 26 aluminum with a half-life of around 0.7 million years. So the idea is if the planetesimals start to accrete within the first couple of million years of the formation of the solar system, they are prone to undergo igneous processes, undergo large-scale melting and differentiation to form differentiated planetesimals. So these baby planets called planetesimals are these differentiated bodies comprising of cores and mantles. And over longer timescales, you have giant impacts amongst these bodies. You go larger and larger. Eventually, you have giant impacts on planetary embryos, and then you have a fully formed planet. So you have this entire protracted accretion history of a planet. So basically, if you really want to understand all of this, you need to track this journey from these very primordial chondritic reservoirs coming from these undifferentiated planetesimals to these fully formed planets. It's a very complex series of processes. And this is, if you put this astrophysical understanding into some sort of a geochemical and a geophysical framework of planet formation. So within the first million years, you have these 100-kilometer sized planetesimals that are formed and heated during 26 aluminum decay. And then so what you have over here is you form these primordial planetesimals, which are just like rubble piles and which are extremely highly porous and permeable. Then you also accrete a lot of 26 aluminum. And when you heat during 26 aluminum, the first thing that you're going to melt in the planetesimal are the ices, which are also going to interact with organics. So you have these supercritical fluids. And because the planetesimal is extremely porous and permeable at this stage, you have this free flow of fluids basically taking place. And then you could have volatile loss during this open system degassing, because again, the system has not sintered down. And eventually, what you would have is that the planetesimal will continue to heating, and whatever volatiles are left inside, then they would participate in these high temperature processes, probably in a magma ocean environment. It doesn't have to be so, but then you would have eventually have the core formation and so on and so forth. And importantly, these processes take place in very small bodies, probably hundreds kilometer sized bodies, and the pressures are in the range of sub GPa range. So these are relatively much lower pressures than many of you guys would be interested in. But these are very important processes. So they're high pressure, but not as high as you would want them to be. And then you have giant impact processes taking place. And in these cases, the metal silicate equilibration and so on and so forth would be taking place at much higher pressures. And depending upon the planetary size, could be up to like 50, 60, 70, 80 GPa if you are focused on Earth. Again, we don't know the exact, but like the pressure where the core metal equilibration took place, but it could be an evolving range that could be at much higher pressures. And eventually, what you would have is when the core formation is complete, then you have exchange of volatiles between the atmosphere and the crystallizing magma ocean. And then you would have the secular evolution once you have a locked system, and then you have evolved over much longer timescales during subduction processes and so on and so forth. So these are again, so what the point I was trying to make over here is there are processes taking place over entire history of the Earth, starting from low pressure processes, going to high pressure processes, and so on and so forth. So what I'm going to today focus on particularly is this planetesimal formation and planetesimal differentiation stage taking place in very small bodies at relatively low pressures. And I'll try to convince you that all of the interesting stuff, or at least most of the interesting stuff related to the origin of volatiles in rocky planets, is actually controlled by these very, very low pressure processes taking place in the first formed planetesimals in the solar system that formed within the first couple of million years of the formation of the solar system. So to now take a step back and try to see, okay, now how do we understand the initial architecture of the solar system to put this broad understanding in some sort of a cosmochemical context? So I'm going to keep things very simple over here. So what you have over here is this fundamental isotopic dichotomy between meteoritic reservoirs that Paul Warren found out 14, 15 years ago. So what this tells us, so on the y-axis, you have the titanium anomalies. On the x-axis, you have the chromium isotope anomalies. So what this kind of tells us is that meteorites plot in two distinct clusters in this isotopic space. So carbonaceous chondrites, likely coming from the outer part of the disk, they sample. These are carbonaceous chondrites sampling the outer solar system planetesimals, and then you have inner solar system planetesimals sampled by the chondrites would be enstatite chondrites and ordinary chondrites over here. So just as a convention, I'm going to follow through this entire talk. Blue always means carbonaceous or the outer solar system. Red would always mean non-carbonaceous and the inner solar system. And if you look closely over here where Earth and Mars plot, what you see closely is what you see over here is that Earth and Mars plot in the inner solar system cluster. And so what it kind of tells us is that Earth and Mars that were mostly made up of inner solar system materials with very small contribution from the outer solar system reservoir. our constraints right now are that probably Earth was made up of 5% of 5% of the Earth's mass was made up of outer solar system materials, while 95% or somewhere close by was sourced from inner solar system materials. Another important point that we need to remember is look at the accretion ages of these chondrites, these very primordial materials. Planet formation models tell us, and if you look at even the growth rate of Mars, we know that the seeds of the rocky planets started to form right at the onset of solar system formation. That is within the first million years of the formation of the solar system, the seeds of the rocky planets started to form. And if you look at chondrite, their accretion ages are rather late. So they might not actually sample the primary building blocks of rocky planets. So in this case, there is another class of meteorites that could come to a rescue in solving this problem. And this class of meteorites are known as iron meteorites. So from iron meteorites, you sample both the earliest form planetesimals, both in the inner and outer solar system reservoirs. And what are iron meteorites? Iron meteorites are the remnants of the metallic cores of the first form planetesimals in the solar system. So basically, to form a metallic core, you have to at least either the cores form through percolation or through in a magma ocean-like environment where you have undergone large-scale silicate melting. The metallic droplets would have equilibrated with the silicate droplets. So basically, then you have eventually formed the core. So the idea is that you're sampling the core, and probably these iron meteorites are sampling the cores, and from these cores you want to reconstruct the entire chemistry of these first planetesimals in the solar system. And as I pointed out earlier, that Earth and Mars are mostly made up of inner solar system materials. That then, if you truly want to understand the compositions of or the volatile compositions of the first form of the building blocks of planets, we need to track the volatile abundance in the isotopic composition of the first form planetesimals in the inner solar system. These iron meteorites that are sampling the inner solar system reservoir. So the general understanding from an astrophysical framework on this particular problem is that within the first million years of formation of the solar system, the inner parts of the disk where these planetesimals should be forming should be extremely hot. So you should not be condensing any volatiles in the solid. So basically, you should be only condensing volatile-free materials in the inner part of the disk, and volatiles should be condensing only in the outer parts of the disk in the form of solids. So the planetesimals that form in the outer part of the disk, they should be volatile rich, but they should be condensing a lot of these water ice. They should be condensing a lot of these organics. But like planetesimals that should be accreting in the inner part of the disk, the astrophysical models tell us they should be almost volatile free. So the idea is if the materials are almost volatile free, then during differentiation, you should not be the metal that is separating out from the silicate magma ocean should not be seeing any volatiles, and eventually you would form cores that should be absolutely free of volatiles. They should not be volatiles in these earliest form cores or these iron meteorites. So the idea is that what do iron meteorites tell us about the origin of volatiles on Earth? What do these first form planetesimals in the inner solar system tell us? Are they carbon or nitrogen free or not? So what you have over here is when you started compiling the data, looking at the carbon contents of these different groups of iron meteorites. So what you simply what so each symbol, each group. So there are these different groups of iron meteorites over here, and each group represents a unique iron meteorite parent body. So what it tells us is that from grouped irons, we have 5 samples from the 5 planetesimals from the inner solar system and 6 from the outer part of the solar system. And red again inner solar system, blue outer solar system. So what do you see over here is that the inner solar system, these inner solar system iron meteorites, they are not particularly more volatile poor than than the outer solar system iron meteorites, than these blue colored meteorites. And in some cases, the red colors contain even more carbon than the carbon that is present in the blue colored iron meteors that come from the outer part of the solar system. And similar kind of story holds true for nitrogen. So basically, which means that these cores contain significant amount of carbon and nitrogen. And if you plot the bulk silicate earth carbon and nitrogen abundances over here, it means that there is significant amount of carbon and nitrogen in these iron meteorites. So as the astrophysical, contrary to the astrophysical models, these first form planetesimals probably were accreting carbon and nitrogen, because that's how we're sampling carbon and nitrogen from the cores of these first form planetesimals in the inner part of the solar system. So the question then arises, then what is the source of carbon and nitrogen in these iron meteorites? So again, the idea is to look at the sources. People generally do isotopic fingerprinting. The issue with carbon is that for carbon, there are very limited measurements in iron meteorites. Again, I can talk in detail why there are limited measurements, but I'm going to go into those details as of now. So for carbon is not very useful in this particular exercise. But when you start to look at the nitrogen isotopic compositions of these iron meteorite groups, you see something really interesting. What you see over here is that the inner solar system iron meteorites, their nitrogen isotopes plot in a completely distinct space relative to the outer solar system iron meteorites. You see this isotopic dichotomy in the nitrogen isotopic space as well. But the important message that it tells us is that the that the first planetesimals in the inner solar system, they were not only accreting nitrogen, but they were also accreting nitrogen from a source that was isotopically distinct from the outer solar system reservoir. So it's not a similar source as the outer solar system bodies. It's a distinct and isotopically distinct source from the outer solar system material. So it kind of tells us is that there definitely was a presence of a distinct volatile reservoir that was present in the inner solar system. And we have and last year another paper where we also talked about the story of water. So I'm not talking about water over here, but you get the same kind of ideas about water, some indirect evidence on water as well. Okay. So if you take a step back now and put these cosmochemical ideas about the origin of volatiles and try to compare it with the terrestrial reservoirs, so over here I have plotted chondrites over here. So what you see is the CC chondrites, the blue colored stuff is generally much more positive. The inner solar system stuff is generally much more negative. Earth's atmosphere is over here. The primordial mantle, probably sampled by pre-datic diamonds, could be much more negative, and they are not as many negative values that you see over here. But generally, it's much more negative. And when you start to plot the iron meteorites over here, you see a similar kind of a thing. The outer solar system iron meteorites, similar to the chondrites, they have their delta 15N values are much more positive, similar kind of a signature. But the delta 15N values of the inner solar system iron meteorites are much, much more negative. So basically, they go up to minus 100 per mil. And if you compare the primordial mantle, it kind of could could also explain the nitrogen isotopic composition of the primordial mantle if it is as negative as sampled by the pre-datic diamonds. But also, it would also imply that if the values of the first planetesimals in the inner solar system, and if they were the basic building block of planets, the nitrogen isotopic composition of the Earth's primordial mantle could have been much more negative, which means that you also need an influx of these 15 enriched carbonaceous materials into the Earth's mantle. So it also has kind of roles into the dynamics of the Earth's growth and so on and so forth. So there are very interesting questions that one could ask from here if the data is telling us if there are no perturbations in the data, if data is actually telling us something about the primordial reservoirs in the early solar system. So now the question ties in is that, okay, you can try to solve these very interesting questions from RN meteorites, but the question is like, how do you make sure quantitatively that what you're measuring from the RN meteorites can actually can be quantified in a better manner, so you have a much better tracking of the volatile inventories of these first from planetesimals just from partial sampling of the cores of these bodies. So what I'm going to try to convince you today is that how do we utilize iron meteorites now to track the origin of volatiles on Earth, try to come up with more quantitative frameworks to understand this problem a little bit better. So what I'm going to try to do is, I'm going to try to talk through two particular questions asked in asked in many different ways. So I'm going to ask is how can iron meteorites be used to reconstruct first the nitrogen and carbon abundances of the earliest solar system planetesimals, and how can we use iron meteorites even to trace the nitrogen isotopic composition of the first form planetesimals in the solar system. Remember, our goal is to go from iron meteorites and reconstruct the chemistry of these first planetesimals, reconstruct the bulk planetesimal chemistry. Because once we do that, we have some sort of handle, because planets are not made up only from the core materials. They're made up of these bulk planetesimals, which comprise of the core and mantle reservoirs and so on and so forth. So the goal is to use this partial sampling of these earliest form planetesimals and reconstruct the entire chemistry of these first planetesimals, because they not only tell us something about what were the volatile budgets of the building blocks look like, but also tells us something about the primordial nebular chemistry that was taking place in the disk. Okay, so then it comes down to the question I was trying to refer earlier, that so this is where the utility of high pressure temperature experiments actually come in to answer these questions over here. So the first way I'm going to do is, how do one utilize high pressure experiments to solve this problem? Because if you look in this particular picture over here, we only are sampling the cores. So what we want to do in these high pressure experiments is we want to use equilibrium elemental partitioning and isotopic fractionation experiments between solid and liquid metal to constrain the effect of core formation, because you have metal silicate droplets exchanging in the magma ocean and forming a core. So we want to retrace that part of chemistry. So you do high pressure temperature experiments that are metal silicate partitioning experiments. So in that, from the core, and if you know the partition coefficient of, say, of nitrogen and carbon between metallic and silicate reservoirs, so once you know the core and you know the partition coefficient, then you can reconstruct the composition of the volatile abundances in the silicate reservoirs. And once you know what the silicate reservoirs look like, once we already know what the metallic reservoirs look like, you can reconstruct the volatile abundances in the bulk planetesimal. And the same thing, because we are also interested in how the nitrogen isotopic compositions behave. So one can also do experiments to understand equilibrium nitrogen isotofractionation between the metallic and silicate reservoirs. We can experimentally constrain this particular parameter, which is the cap delta 15N difference between metal and silicate reservoirs. And we already know the nitrogen isotopic composition of the alloy, so we can constrain this particular number. And once we know this, then we can reconstruct the entire the bulk chemistry of the entire not only the nitrogen and carbon abundances of the bulk planetesimal, but also the isotopic composition of the nitrogen isotopic composition of the bulk planetesimal. And there is another set of experiments one can also use to understand the core chemistry a little bit better, because the reason is iron meteorites come from this fractional crystallized core. So one can use the equilibrium elemental partitioning and isotopic fractionation experiments, but now between solid and liquid metal, because you're interested in the core crystallization. So why is that particular fact important is because when you form a core, the core would eventually go core crystallization. And what we know from our iron meteoritic record is we are not sampling the entire cores. We are only sampling certain regions of the cores, and some regions of the cores are unsampled in our iron meteoritic record. So the idea is to use the iron meteoritic record and high pressure experiments to reconstruct the bulk chemistry of the entire core. Say, for example, in group 2C, a given core, we are only sampling the first 30% of the fractional crystallization sequence, while for group 2D, we might be sampling 80 to 90% of the fractional crystallization sequence. So one only has a partial sampling of the core reservoirs as well. So to reconstruct the chemistry of the entire core, one needs to constrain how elements and isotopes fractionate between the solid and liquid metal. Just again, so basically you have partial sampling of the core. From the partial sampling of the core from the iron meteorites, you want to go the full chemistry of the core. Once you know the entire chemistry of the core, then you can use metal silicate stuff to actually constrain the chemistry of the entire planetesimal. So this is a series of steps that one needs to follow to get the volatile abundances and the isotopic compositions of the building blocks of planets. And why is the core crystallization part important? As you expect, the cores are primarily made up of iron, nickel, but there is a very important non-metal that could be a major component of these cores and that component is sulfur. So basically, why is sulfur important? So basically, when you do fractional crystallization sequence, so you start to sequentially grow the core or crystallize a core. Sulfur never partitions into the solid metal, which means that the residual liquid will keep on getting enriched more and more in the sulfur. So for example, if you start with a core that initially contained 10 weight% sulfur, and if the core has undergone 50% crystallization, then the residual liquid will contain 20 weight% sulfur. So initially, when you're crystallizing the metal, you're partitioning between solid metal and a liquid metal containing 10 weight% sulfur, eventually 11, 12, 13. So basically, that's how you need to reconstruct as a function of sulfur content in the liquid metal to reconstruct the composition of the entire core. So basically what we have is the sample regions of the cores are almost sulfur free, and and the sulfur rich regions we are not sampling in our iron meteoritic record. And so this is where the high pressure temperature experiments come in, because we can simulate these experiments and try to understand how carbon and nitrogen partition between solid and liquid metal. We know the iron meteorites. Once we know the partition coefficient, then we can reconstruct what did this unsampled portion look like, and then we can reconstruct the composition of the entire core. And the same game can be played with the nitrogen isotopic fractionation between solid and liquid metal. So you can do these kind of interesting experiments and try to tease out the right thermodynamic parameters that even if you have partial sampling of some meteoritic record, you can actually reconstruct the entire in the entirety of even the unsampled record. So to do this, to reconstruct the effect of the fractional crystallization of a core, again, what you do is experiments between solid and liquid metal. So these experiments in a couple of my studies that I did with Paul at Caltech was we simulated not only carbon and nitrogen element fractionation between solid and liquid metal, but also nitrogen isotopic fractionation. These experiments were done at low pressures around 0.1 GPa. Ideally, we should have gone much lower, probably using IHPV that is present at force, but we did these experiments at 1 GPa, and the sulfur content of the liquid metal was varied between 0 and 38%. So this is a typical experimental product over here. This is a solid metal, you have a liquid metal, and then these experiments were done with different amounts of sulfur in the liquid metal. And you can measure carbon partitioning, elemental partitioning between carbon and nitrogen, elemental partitioning between solid and liquid metal, and one can also measure the nitrogen isotopic fractionation. For elemental abundances, one can use in situ techniques like electron microprobe analysis. For nitrogen isotopes, we separated out both of these phases, crushed them, and then measured the nitrogen isotopic compositions of each phase using IRMS. So this is a destructive technique. So what do we get from our experimental data? So these experimental data represent the nitrogen and carbon partitioning between solid and liquid metal as a function of sulfur content in the liquid metal. So this is D value, which is concentration in the solid divided by liquid. So what you see over here is when the sulfur content on the liquid metal is low, nitrogen and carbon are incompatible in the solid metal, but as the sulfur content of the liquid metal keeps on increasing, nitrogen and carbon become more and more compatible in the solid metal. So this behavior is primarily related to the activity coefficient of carbon and nitrogen in the liquid metal as a function of sulfur content in the liquid metal because of non-ideal interactions between carbon and nitrogen with sulfur. So nitrogen and carbon become more and more incompatible in the liquid metal, so they start to partition into a solid metal as the sulfur content of the liquid metal keeps on increasing. And the important point over here is because the unsampled regions of our RN meteoritic record for these given cores are these regions. So we are only what we need is we need these thermodynamic values, these partition coefficient and high sulfur contents to actually constrain what were the carbon and nitrogen contents in the unsampled parts of the cores. So if you look at carbon, the carbon partitioning between solid and liquid metal at even very high sulfur content, these numbers stay very close to 1. So what it tells us is that the carbon contents in the unsampled parts of the cores were a little bit lower than carbon contents in the sample parts of the core. You're not missing by that much. But for nitrogen, as nitrogen becomes very incompatible in the solid metal, so basically the nitrogen contents in the unsampled parts of the cores are much lower than the nitrogen contents in the sample parts of the core. To put simply, what it would mean is that the carbon contents of the iron meteorites are probably sampling the carbon content of the entire core because carbon partitioning between solid and liquid metal is not very sensitive as a function of sulfur content. But as nitrogen partitioning is very, very sensitive, the nitrogen contents in the unsampled parts of the cores are much lower than the nitrogen contents in the sample parts of the cores. So what that would mean is if you're exclusively using iron meteorites to reconstruct the nitrogen abundance in the core, you are actually overestimating. The nitrogen content in the core, the fully formed parent cores could be actually lower than what is sampled by the iron meteorites themselves. So these are interesting constraints that one can bring into play. Similar things one could play with how nitrogen isotopes partition between solid and liquid metal. So one can see over here is the cap delta 15, and so this is a nitrogen isotopic difference between the solid and liquid metal as a function of sulfur content in the alloy melt. And you see this number keeps on increasing. It's kind of like a weak correlation one that one sees over here. Is kind of also related to the activity coefficient of nitrogen and the sulfur content in the liquid metal. But the point is that cap delta 15 and value, the nitrogen isotopic difference between the solid and liquid metal is within 1 per mil. It's not very large. There is fractionation, but it's not very large. And the point I'm trying to make over here is if you look at the nitrogen isotopic variation between different groups of iron meteorites, it's on the order of tens of mil, so per mil. So basically, if you go from here, -100 to plus 150. This is the range of variation and you see in different groups of iron meteorites. And the nitrogen isotopic fractionation between solid and liquid metal is actually much more limited. So what you get is that the nitrogen isotopic composition of the iron meteorite parent of iron meteorite groups are probably just identical to the nitrogen isotopic composition of the parent cores. What this means is that iron meteorites faithfully record the nitrogen isotopic composition of the parent cores. But for abundances, the story is a little bit different. And once one gets a handle of both the nitrogen and carbon abundances in the core and the nitrogen isotopic composition of the core, now one can use the core composition to reconstruct the chemistry of the bulk. And in this case, as I was talking about, the metal silicate partitioning stuff comes in. So you can now one needs to use the nitrogen and carbon partitioning between metallic and silicate metals. And one can also constrain the nitrogen isotopic fractionation between metallic and silicate metals. Because once we know all of these, then we have a very good handle on the chemistry of the bulk planetesimal. What did it actually look like? So these experiments have been done over the last few years, or the last 15, 20 years, over much higher range of pressures and temperatures. And this is a typical experimental product. Once again, for these kind of experiments, you have a metallic alloy over here, which is analog of the core. You have a silicate glass, quench silicate glass over here, which is an analog of the magma ocean. And one can measure nitrogen and carbon abundances again during in situ techniques like electron microprobe and SIMS. And the nitrogen isotopic compositions were measured by IRMS because we wanted to get a very high precision numbers over here. I just presented the data, but this is data has been collected over a lot of years, over a huge parameter space on nitrogen and carbon partition between metal and silicate metals. And over here, I plotted the data as a function of the redox state of differentiation. And in a recent study last year, we also constrained the oxidation state of iron meteorite parent bodies. So if I plot this range over here, we see that both carbon and nitrogen act as siderophile elements during core mental differentiation, which is pretty good in the sense that most of the nitrogen and carbon that is present in the bulk planetesimal should be present in the cores of these bodies during core mental differentiation. Most of the nitrogen and carbon partition into the cores, and the mantles should be extremely carbon and nitrogen poor. And for one can do also similar kind of experiments to constrain the nitrogen isotopic fractionation between metallic and silicate metals. So these are experiments I did a few years ago, and these are some time series experiments just to illustrate what kind of data one can get. So over here, you see that experiments were done at a certain pressure and temperature as a function of time, just to see how good our experimental results are. Are we reaching equilibrium and so on and so forth? And the delta 15N values of the alloys are plotted over here in every given experiment. The delta 15N values of the silicates are plotted over here. And you see there is consistently 1 per mil difference between the nitrogen isotopic composition of the metallic and silicate reservoirs. The metal is always lighter than the silicate reservoirs. And these experiments were conducted over higher pressures at different temperatures. And one kind of gets a similar kind of a story. One can start to compile all these data together, and this is the nitrogen isotopic difference between the metallic and silicate reservoirs, and you see consistently a range between around 1 per mil. And note that these experiments were done at a fixed oxygen fugacity. So when you cover these experiments of a much larger oxygen fugacity range, then you start to see these subtle trends in the data, and which is most likely related to the speciation of nitrogen in the silicate metals. I can talk in detail about it later. But the broad story is that the fractionation could lie between, say, 1 per mil to up to 4 per mil. That is the difference between the nitrogen isotopic composition of the metallic and silicate metals. But the important point to remember is nitrogen is so siderophile that even this isotopic difference won't make a lot of difference because most of the nitrogen would be stored in the core of the body. And again, I wanted to reinstate the point over here. The variation which we see amongst the different planetesimals is much larger than the minute differences that you see during these reservoirs. And what it kind of tells us, what it kind of tells us, if you look at the iron meteorites and then try to reconstruct the nitrogen isotopic composition of the core after doing all these numerical calculations, you see that the nitrogen isotopic composition of an iron meteorite group is almost identical to the nitrogen isotopic composition of the bulk planetesimal. So that gives us very good confidence that the nitrogen isotopic composition of iron meteorites are almost identical to the nitrogen isotopic composition of the bulk planetesimal during core mental differentiation, which also tells us that the iron meteorites also faithfully record the nitrogen isotopic composition of the bulk planetesimals. So this is basically how one can utilize all this experimental data. And what are the implications? I'm not going to go deeper into the implications. There's a couple of very important implications that one can have. Remember what we started from was we were using, people mostly have used a quantitic record over the last few decades to reconstruct the origin of volatiles in the earth. What they found out was that the isotopic composition of the volatiles in the bulk silicate earth are similar to that of chondrites. But on the other hand, the volatiles in the bulk silicate earth are extremely depleted by 2 or 3 orders of magnitude. We didn't understand very well what is the cause of this volatile depletion. There are many processes that have been explained. Either the major building blocks of the earth did not accrete volatiles, or the volatiles were lost during giant impacts, and so on and so forth. But what kind of answers, what kind of interpretations one can implications one can come at if you use the iron meteoritic record over here? So again, coming back to this particular picture over here, we see that the delta 15N values of the inner solar system iron meteorites, we sampled the first form planetesimals in the inner solar system, which were likely the basic building blocks of rocky planets. The delta 15N values are much more negative, even much more negative than the most negative value that has been measured in the Earth's primordial mantle, which is by the periodic diamonds. So it has two important implications. So basically, what it would mean is that if the values are so negative, then it will also mean that you need an influx of carbonaceous materials into the Earth's interior to explain the nitrogen isotopic composition of the Earth's mantle, which is not as negative as the nitrogen isotopic composition of iron meteorites. And also importantly, could potentially mean if Earth is primarily made of these kind of bodies, and most of the nitrogen is stored in the core, that the Earth's core could actually also have a much more negative number than that of the Earth's mantle. Both of these reservoirs could be in disequilibrium. Another important point over here is then about the volatile abundances and where did this volatile loss take place. So over here you have the carbon abundances in chondrites, and carbon and nitrogen and carbon and nitrogen in the entire bulk planetesimals. And over here you have different estimates of the bulk silicate earth values over here. And if you focus over here, you see that the chondrites are actually much more volatile rich than that of the iron meteorite parent bodies. So iron meteorites are depleted. The iron meteorite parent bodies, so the first form planetesimals, are depleted relative to these chondritic reservoirs. I have talked about this problem in detail in several of my papers, but the basic idea is over here that you accrete these first form planetesimals. And Megan has also worked on the water part. I have mostly worked on the nitrogen and carbon part of this. So basically, the idea is that you create these first form planetesimals, and these planetesimals would be highly porous and permeable. And these planetesimals could undergo open system degassing and lose a lot of these volatiles during these before you undergoing differentiation. And we have constrained this number that 99% of the carbon and nitrogen can be lost during this open system degassing during differentiation. So basically what it tells us is that the thermal metamorphism processes that are taking place in these earliest form planetesimals in the early solar system, they are the primary cause of the result. They are the primary cause of the volatile depletion of rocky planets in the solar system, including Earth. It is not that the volatiles were not condensing in the inner part of the disk. It's not that other processes. It is primarily because these planetesimals are accreting early enough. You have a lot of 26 aluminum, and before the planetesimal sinter, you have large scale volatile loss, and eventually you would result in planets that are always much more volatile depleted than the primitive chondritic materials. So with this, I'll leave these few key take-home messages, what one can learn when combining high-pressure experiments with very unique kind of meteorites like iron meteorites to reconstruct the origin of volatiles on the Earth. That volatiles were likely available during the entire accretion history of the Earth. I have a recent paper where we also showed this story not only for highly volatile elements, but this story also holds true for moderately volatile elements. Volatiles in the Earth originated from both the inner and outer solar system materials, because it's not exclusively an outer solar system source, because the inner solar system materials, they not only have nitrogen and carbon, but the volatile isotopic composition retains a memory of those materials as well. And that the volatile depletion in the Earth is likely related to volatile loss processes that take place in these very, very small bodies, which lose volatiles very, very efficiently before you start to form larger rocky bodies. Thank you.
Thank you, Daman. And everyone, as I posted, if you have questions, you can put them in the Q&A and I'll read them out loud, or you can raise your hand also to ask a question. Okay, we have a question from Maitri Ghosh who asks, Are there any theoretical simulations to support these experimental data?
Are there any? Which simulations?
Theoretical simulations?
Yes. We think we for the nitrogen isotope fractionation between metallic and silicate melts, we did a bunch of theoretical calculations. And they actually support what our experimental data shows. I'll just quickly show you the what the theoretical calculations are telling us. Yeah, I think I can just share the screen right now. So basically,
Oh,
I
the
work with
sharing. There we go. There it is.
yeah. I work with Edwin Schobel with these calculations. So basically, we have an idea about the speciation of nitrogen in the silicate mill. So we calculated this equilibrium isotope fractionation factors of beta values for nitrogen in different phases. And what you see over here is once you have these factors, you see that the nitrogen isotopic composition of the metal is always lighter than the silicate phases. And that's what we see in the experimental data as well. And if you plot the nitrogen speciation, what we observe from FTIR and Raman analysis as an analog of the FO2, you kind of see a similar kind of a trend as you go as at more oxidizing conditions. The nitrogen isotopic fractionation is on the orders of 4 per mil, which we see from our experimental data. And as you go to more and more reducing conditions, these numbers drop down to around 1 per mil, which we see at the more reducing conditions. So these are at almost like perfect prediction with the theoretical calculation. So this kind of tells us is that from our experiment, we are accurately constraining the equilibrium fractionation of nitrogen isotopes between metallic and silicate melts.
Okay. Any other questions? You say you can go ahead and unmute yourself.
I think if I remember correctly, that you based on nitrogen isotope fractionation between the metal and the silicate, and you predicted the nitrogen isotope content in the bulk uh, material for the inner solar system and the outer solar system, and then even basically the difference between the two materials based on the observation is even higher, maybe 300, 400 per mil or something. Uh, I'm not sure whether I remember correctly.
Yeah, so basically, if you look at, okay, let me bring down to this plot over here. Actually, if you look at the range that the iron meteorites capture is actually pretty significant. They capture a range from minus 100 per mil to almost 150 per mil, and these numbers are as high as what you measure in CR chondrites, and the negative range is even much lower than what you measure in chondrites. Only CB chondrites have actually delta 15 values that are as high as 800 per mil, but CB chondrites are formed to a very specific mechanism, so they don't sample the primordial reservoirs in the solar system. So what it kind of tells us is that iron meteorites also faithfully capture the variation in the nitrogen isotopic composition of the earliest planetesimals, and the range is as large or even larger than what is sampled by chondrites. And again, in the same direction, the outer solar system always 15 and rich, the inner solar system always be 15 and poor.
Okay. Any questions from the audience? If not, then thank you, Daman, for giving your last talk of the semester.
All right, thank you.
Thanks everyone for joining us. See you in the fall.